Hello, and welcome back to the Quantum Slumber. Tonight, I want you to picture something simple. You're holding a flashlight. You press the button, and a stream of light tears out into the dark at 299,792,458 meters per second. Now, here's the part that should make you pause. Light has zero rest mass, zero nothing. It doesn't weigh anything. There's no air in space, no friction, no resistance. So, let me ask you, plainly, why isn't it infinite? What invisible wall is light crashing into, in the emptiness between stars? Because when you throw a baseball, it slows down for obvious reasons. Mass, drag, gravity. But a photon has none of that. It's massless. It's pure motion. So why does it stop at that exact number, every single time, everywhere in the universe? Here's the twist, and it's going to rewire how you see reality. Light doesn't have a speed limit, the universe does. That number isn't a quirky fact about photons. It's written into space and time themselves. And once you see it, you'll understand three things that most people never fully absorb. Why nothing with mass can ever reach that speed, why time is not as fixed as it feels, and why this cosmic speed limit might be the only thing keeping cause and effect, reality itself, from collapsing into chaos. Now, if you want more journeys like this, deep physics, clear explanations, and the kind of ideas that linger in your mind, take a second to like the video and subscribe to the channel. And I'd love to hear from you. What country are you watching from? And what time is it right now? Are you here late at night, wide awake, or sneaking this in when you're supposed to be doing something else? All right, let's begin with the simplest question that isn't simple at all. What is light? Light is one of those words we think we understand, because we live inside it. Sunlight through a window, a phone screen in the dark, the soft glow of a street lamp on a rainy night. But if I ask you what light actually is, not poetically, not metaphorically, but physically, your intuition starts to slip. Here's the answer that sounds insane the first time you hear it, and yet it's simply true. Light is both a particle and a wave, at the same time, always. Not sometimes a wave, not sometimes a particle, not it switches back and forth depending on mood. It behaves like a ripple spread out across space, and like a tiny localized projectile that arrives in discrete hits. And the fact that those two descriptions can both be correct is one of the deepest hints that reality does not operate the way our brains expect it to. A little over a century ago, most scientists were convinced light was purely a wave. It made sense. Waves explain reflection, refraction, interference, how light bends through glass and paints rainbow colors in a prism. Waves were elegant. Waves were comfortable. Then in 1905, a 26-year-old patent clerk named Albert Einstein published a paper that disrupted that comfort in a single stroke. He wasn't a professor at some grand university. He was working a day job in Bern, Switzerland, reading inventions other people wanted credit for. And in his spare hours, he was rewriting the rules of nature. Einstein was trying to explain a stubborn mystery called the photoelectric effect. If you shine light on certain metals, electrons pop out. But the weird part wasn't that electrons came out, it was how they came out. Brighter light didn't necessarily do the trick. What mattered was the type of light, the frequency. Below a certain threshold, you could shine a light forever and nothing would happen. Above it, electrons were ejected immediately. That behavior makes no sense if light is only a smooth wave. A wave should be able to deliver energy gradually, like pushing a swing higher with repeated nudges. But that's not what the metal was doing. It was acting like it needed a single, sharp hit. So, Einstein proposed something radical. Light comes in discrete packets of energy, not continuous flow. Packets, quanta, what we now call photons. In other words, light can behave like tiny bullets, each one delivering a specific amount of energy in a single impact. That idea didn't just explain the photoelectric effect, it helped launch quantum mechanics itself, and it eventually earned Einstein the Nobel Prize. At that point, you might think the mystery is settled. Light is a particle, case closed. except reality doesn't let you close the case. Because long before Einstein, back in 1801, an English scientist named Thomas Young had already performed an experiment that makes light as particles feel impossible. He sent light through two narrow slits and watched what appeared on a screen behind them. If light were just particles, you would expect two bright bands, one for each slit, like two streams of tiny pellets. But what Young saw was an interference pattern, alternating bright and dark stripes, the unmistakable signature of waves overlapping, reinforcing, and canceling each other out. A particle doesn't cancel another particle into darkness. A wave does. So now you're trapped between two facts that are both experimentally real. Light arrives in discrete impacts like particles, and it spreads out and interferes with itself like a wave. And that's the point. Light isn't either /or in the way our brains want it to be. It is the first thing most of us encounter that forces us to admit the universe is not obligated to match human intuition. The deeper truth is that what we call a photon is not a little marble flying through space. And what we call a wave is not just a watery ripple. It's something stranger, a single entity that reveals different faces depending on how you look at it, yet remains one thing. And now we can say something that sounds small, but will matter for everything that comes next. These photons, these packets of light, have zero rest mass. Not almost zero, zero. Which means whatever is enforcing that precise speed, it isn't drag, and it isn't weight. So if light is this paradox, wave and particle, massless yet real, then we're right back at the original question, only sharper now. What exactly is stopping a massless thing from going infinitely fast? Now, let's take the most common misunderstanding and crush it cleanly. When people hear photons have zero rest mass, their brain quietly substitutes a different sentence. Photons are nothing, as if light is some ghostly placeholder in the universe, a kind of empty shimmer. But massless does not mean powerless. It does not mean weightless equals harmless. It does not mean no substance equals no impact. A photon has zero rest mass, meaning it can't sit still and still be a photon. It doesn't have a rest frame where it's just hanging out, quietly existing with a little label that says mass. If you could somehow chase a photon and match its speed, you don't arrive next to it and inspect it like a marble in your hand. You never catch up in that way. That's what massless really implies. And yet, the moment that photon hits something, the universe reacts as if something very real just happened, because it did. A photon carries energy, and it carries momentum. That second part, momentum, still trips people up, because we associate momentum with mass, with heft, with weight. A bowling ball has momentum because it has mass and it's moving. A truck has momentum because it's heavy and it's fast. So, the idea that a massless thing can have momentum sounds like a contradiction, but physics doesn't care what feels intuitive. For light, energy and momentum are inseparable. If a photon has energy, it has momentum. It can deliver a shove, a tiny shove, but a real one. That's not philosophy, it's engineering. Solar sails work because of this. A solar sail is basically an ultra-thin, reflective sheet in space, and sunlight pushes on it. Not with gusts like wind, with radiation pressure, photons striking the surface and transferring momentum. It's almost insulting how small the force is per square meter. And yet, in the vacuum of space, with no air resistance and no engine burn, that tiny continuous push adds up. Over days, weeks, months, it becomes motion you can measure. Course changes you can plan. A spacecraft that slowly accelerates, powered by something that has no rest mass. So, stop and let that land. Massless particles are physically pushing on material objects. That's happening in your universe, right now. And it's not just solar sails, it's everything light touches. Photons deliver energy to your skin, they heat surfaces, they trigger chemical changes, they knock electrons loose in solar panels, they carry information through fiber optic cables. They are the reason you can see anything at all. This is why massless is such a dangerous word if you treat it like empty, because the real twist is that photons don't need mass to matter. They're not weightless nothingness drifting through space. They are discrete packets of energy moving with relentless precision. And when they arrive, they don't arrive as a suggestion. They arrive as an interaction, an exchange, an event. Which brings us right back to the problem that refuses to go away. If photons have no rest mass, and if empty space isn't slowing them down with friction or drag, then why do they move at one exact speed? Why not faster? Why not infinite? Here's where the conversation stops being about a fast thing and starts being about the rulebook reality is forced to obey. Because if you zoom out far enough, you realize something uncomfortable. Space is not just a stage where events happen. Space is part of the mechanism that decides what events are allowed to happen at all. We like to imagine the universe like an empty box. Drop something in, it moves. Turn on a flashlight, it beams across the box. Simple. But the box isn't empty, and it isn't passive. Space and time are welded together into a single structure, space-time, and that structure has a built-in constraint. There is a maximum rate at which influence can spread, not objects. Influence, cause, and effect, signals, information, energy, anything that could physically count as A leads to B. That limit is what we call C. And this is the key reframing most people never get. Light doesn't choose to travel at C like it's obeying a speed limit sign. Light is what you get when the universe is doing something at the maximum allowed rate. It's the fastest possible way for a change over here to become a change over there. So, when people say the speed of light, what they're really naming is the speed of causality, the speed at which reality can update itself without breaking its own logic. If that sounds abstract, good. It should. Because what you're staring at is the boundary line between physics and nonsense. Imagine you could send cause and effect instantly, not very fast, instantly. Then distance would stop meaning anything. A star exploding 100,000 light years away could affect you right now, with no delay. Your present would be infected by events with no time separation. There'd be no clean ordering, no reliable before and after across space. And if you can't reliably order events, you can't reliably define what it even means for one thing to cause another. That's not just inconvenient, it's fatal to the idea of a universe that can be described at all. So, space-time enforces a maximum propagation in speed the way a computer enforces a clock rate. It's not a preference, it's architecture. This is why relativity isn't some optional add-on, like a weird chapter at the end of a physics textbook. Relativity is what you get when you take that speed limit seriously and refuse to let logic collapse. Because the moment you accept there's a maximum speed for influence, you get a strange geometry of what can reach what. In space-time, every event has a kind of boundary, an invisible region of permission. There are things that can be affected by it, and things that cannot. Not yet. Maybe not ever. Your now isn't a universal slice shared by the whole cosmos. It's local. It's private. Two people separated far enough can disagree on what counts as simultaneous. And the universe doesn't consider either one of them wrong. That sounds like a philosophical crisis, until you realize it's the only way to keep causality from tearing itself apart. And suddenly, C stops feeling like a random number and starts feeling like a safety rail. A guardrail that says, you are allowed to have a universe with distance, sequence, history, and consequences. But in exchange, nothing gets to send a physical message faster than this. Notice what that implies. The speed limit is not about light. It's about information with teeth, anything that could carry a real influence. Light just happens to be the cleanest, simplest messenger that lives exactly on that boundary. And there's a reason this idea feels so solid to physicists. The universe has given us real-world, brutal, time-stamped demonstrations that this limit is woven into the structure of events, not into the personality of a particular particle. One of the most haunting examples is a supernova called SN 1987A. A massive star collapsed in a neighboring galaxy, and the catastrophe released an enormous burst of neutrinos, those almost ghost particles that barely interact with matter, followed closely by light. Here's what makes that story perfect for this moment. Neutrinos are not photons. They are not light. They have their own properties, their own weirdness. They pass through stars like they're mist. And yet, after traveling for an absurd span of time across intergalactic distance, the neutrinos arrived only a short window before the light did, like two different messengers obeying the same cosmic timing constraint. It's as if space-time is saying over and over, this isn't a rule for photons, this is a rule for the universe. And once you see it that way, the original question starts to transform. We're not asking, why is light capped? We're asking, why does space-time have a maximum update speed at all? And if you're wondering why that maximum has the value it does, why it's that number and not another, good. Because the next step is where the universe stops sounding poetic and starts sounding like math that accidentally revealed a secret. Here's the moment where the universe basically confesses what it's made of, without meaning to. Because C didn't start as a sacred number carved into a stone tablet. It wasn't discovered by watching a photon with a stopwatch. It fell out of math. In the 1860s, a Scottish physicist named James Clerk Maxwell was trying to do something that sounds modest and ends up rewriting reality. He wanted electricity and magnetism to stop being two separate mysteries. Before Maxwell, people knew electric charges did strange things. Magnets did strange things, and wires could make compasses twitch. It felt like a messy collection of tricks. Maxwell turned it into a single system. He wrote down a set of equations, 4 statements that describe how electric fields and magnetic fields behave, how they create each other, and how they change through space. And then something happened that should still feel illegal. When you combine those equations, you don't just get fields, you get a wave. A self-sustaining ripple. An electric field changing creates a magnetic field, and a magnetic field changing creates an electric field, and the whole pattern propagates forward like a perfectly timed relay. And when Maxwell calculated the speed of that wave, he got a number determined by 2 constants, values that describe the vacuum itself, how easily electric fields form in empty space, and how easily magnetic fields form in empty space. That matters, because it means empty space isn't nothing. The vacuum has electrical and magnetic properties, quiet, invisible parameters that set the pace of reality. So Maxwell does the math, and a speed appears, a fixed speed, a speed that doesn't depend on the source, doesn't depend on the observer, doesn't depend on the wave being tired or pushed harder, just a built-in propagation speed for electromagnetic disturbances. And that speed matched the measured speed of light, which is the kind of coincidence that stops being a coincidence the moment you understand what it implies. Light isn't some special substance racing through emptiness. Light is what an electromagnetic wave looks like when the universe runs it at the vacuum's natural propagation speed. That's why the number is so stubborn. It's not a speed limit invented for light. It's a speed dictated by the structure of the vacuum itself. This is also why people talk about C like it's foundational. Maxwell essentially showed that if you allow electric and magnetic fields to exist at all, if you allow the vacuum to have these properties at all, then a maximum wave speed is baked in. And once Maxwell's prediction was on the table, physics gained a new kind of confidence. Because it wasn't just storytelling, it was a forecast. A few decades later, experiments created and detected these waves directly. Radio waves, proving that Maxwell hadn't just built a pretty theory. He'd uncovered a real mechanism operating in the world. But here's the catch. The thing that makes this discovery so powerful is also the thing that makes it dangerous. Because if Maxwell's equations say electromagnetic waves travel at one specific speed in vacuum, then that speed shouldn't behave like normal speeds. Normal speeds add and subtract depending on how you're moving. And if this speed refuses to play that game, you don't just learn something about light. You learn something about space and time. And that's where the simple idea of a constant speed turns into a problem that forces the universe to rewrite the rules of motion. Here's the core move that relativity makes. so clean it almost feels like a scam. You don't just move through space, you move through space-time. And you only get so much motion to spend. Spend more of it on getting somewhere fast, and you spend less of it on aging. That sounds like poetry. It's not. It's accounting. Think about your life like a path you're tracing through the universe. Not a path on a map, more like a path through a four-dimensional grid where forward in time is part of the direction you're traveling. Even when you're sitting still, you're still moving, because you're moving into the next moment. That's the default motion every object has. Now, start moving fast through space, and something weird happens. Your path tilts. You're not adding speed on top of time like they're separate dials. You're redistributing how your motion is oriented, and the universe keeps the book with one rule. The total speed through space-time is fixed. This is why time dilation isn't a mechanical slowdown, like a clock getting sticky. It's geometry. It's the shape of your trajectory. So, when people say, a fast-moving clock runs slow, they're not saying the clock is broken. They're saying the clock is honest. It's measuring its own time, its proper time, and proper time depends on the route you take through space-time. That's the first punchline. The second punchline is that we don't believe this because it's elegant. We believe it because the universe keeps humiliating anyone who tries to ignore it. In 1971, physicists Joseph Hafele and Richard Keating took atomic clocks, real, precise, stubborn clocks, and put them on commercial airplanes. Not rockets, not sci-fi, planes. They flew them around the world and compared them to clocks that stayed on the ground. If time were absolute, all those clocks should agree, because a second should be a second everywhere. They didn't. The flying clocks were offset by measurable amounts, in the exact direction relativity predicted when you include two effects at once: motion, special relativity, and altitude in Earth's gravitational field, general relativity. The numbers weren't huge, they were tiny. But that's the point. Reality didn't sort of do relativity. Reality did it precisely, quietly, like it was never optional. And if you want an even more brutal proof, you're probably holding it in your hand. GPS works because engineers treat time dilation like a maintenance fee the universe charges. Satellites are moving fast compared to you. That makes their clocks tick a little slower, but they're also higher up in Earth's gravity, which makes their clocks tick a little faster compared to clocks down here. Both effects are real, both are measurable, and if you don't correct for them, GPS drifts fast, not eventually, fast enough to become useless. So, when you see your location on a map, you're watching a technology that only functions because we admitted something that sounds insane. Time is not universal. Time is local. You don't get handed the present. You carry your own. Now, here's where it gets truly unsettling. If motion changes time, then now becomes a negotiation too. Two people moving relative to each other don't just disagree about how fast each other's clocks run. They can disagree about what events are happening at the same time. That's not philosophy. That's a direct consequence of keeping the speed limit consistent for everyone. Because if the speed of causality is fixed, then you can't have a universal sync that works in all frames without breaking that rule. So, the universe makes a trade. It protects the speed limit by letting simultaneity bend. That's why relativity doesn't say, nothing can go faster than light as a random restriction. It says something sharper. If you could send cause and effect faster than that limit, you could scramble the order of events for some observers. You could build paradoxes. You could create a universe where because stops meaning anything. The speed limit isn't a performance cap. It's the rule that keeps logic from tearing. Now bring that back to the weirdest character in this story, the photon. A photon is massless, and massless things don't get the option of traveling slower than the limit. They live on the edge. Here's the mindbender. In relativity, different paths through space-time have different amounts of proper time along them. For objects with mass, like you, your path is time-like. You always experience time passing. You can't opt out. But light follows a light-like path, and along a light-like path, the proper time is 0. That's not a metaphor. That's the math. So people sometimes say, From the photon's perspective, time doesn't pass. You have to be careful with that phrase, because a photon doesn't have a rest frame in the way a massive object does. You can't hop on a photon like it's a train and do normal clock comparisons. But what you can say, cleanly, safely, and with full authority, is this. If you measure time the way the universe measures it along trajectories, the amount of proper time available to a photon between emission and absorption is 0. Meaning the universe doesn't assign aging to that journey. A beam could cross a galaxy, bounce through interstellar dust, skim past a black hole, and arrive at a telescope millions of years later. And that path still has no proper time stamped on it. So in the accounting system of spacetime, light is the extreme case. Maximum spatial motion, minimum proper time, pushed all the way to the boundary. And that boundary is exactly the speed limit we started with, which sets up the next unavoidable question. If that edge is where time thins out to nothing, why are only massless things allowed to live there? Why does adding even a tiny bit of mass suddenly make the universe demand an impossible price to reach it? There's a brutal rule hiding inside that beautiful idea of a speed limit. If you have mass, you can chase the edge forever and never touch it. Not because the universe is being dramatic. Because the closer you get, the more the universe changes what your effort even means. Here's the mistake most people make. They imagine speed like a gas pedal. Press harder, go faster. Keep pressing, eventually you hit the maximum. That's how it works in everyday life, because we live in the slow motion regime of physics. At highway speeds, adding energy mostly shows up as more speed. The math is gentle, the universe is forgiving. But the moment you start approaching the speed of light, the accounting system flips. Energy stops behaving like more miles per hour. Energy becomes resistance to acceleration. It's not that your engine becomes weaker. It's that space-time starts charging you more and more for every extra fraction of speed you try to buy. And the price doesn't rise linearly. It rises like a wall. You can feel the idea without equations. You push, you accelerate, everything seems normal. And then, as you near the limit, the same push yields less and less added speed. It's as if motion itself gets stiffer. Like the universe is tightening the steering wheel the closer you get to the edge. This is why people used to talk about relativistic mass, as if your mass literally increases. Modern physics usually avoids that phrase because it can confuse what mass means. But the intuition it tried to capture is real. As your speed climbs, your momentum becomes harder and harder to change. Your inertia becomes more expensive. So, what does your added energy go into if it's not giving you much more speed? It goes into the total energy of the system, into the curvature of how your motion sits inside space-time. It becomes more and more locked into the geometry. You're pouring energy into a system that refuses to let velocity cross a boundary, so the energy piles up in every other way it can. This is the infinite energy wall. Not a metaphor, a literal statement. To reach the speed of light with any object that has rest mass would require infinite energy. And infinity isn't a really big number. Infinity is the universe saying, not allowed. Now, if you want this to feel real, if you want it to stop sounding like a clever trick, there's a place on Earth where humans have basically been screaming at this wall for years. Particle accelerators. At CERN, in the Large Hadron Collider, they take protons and push them with electromagnetic fields over and over and over, feeding them energy like it's a ritual, and the protons respond in the most disrespectful way possible. They do get faster, but not by much. After a certain point, they're already so close to the speed of light that adding enormous amounts of energy barely nudges their speed at all. Instead, what changes dramatically is their energy and momentum. The oomph of the proton skyrockets. The damage it can do skyrockets. The bookkeeping value of that particle, how much energy is riding inside its motion, becomes monstrous. But the speed, it creeps and creeps and creeps, always approaching, never arriving. That's not a philosophical argument. That's engineers reading instruments. So, when you hear nothing with mass can reach the speed of light, You should picture a real machine, in a real tunnel, pushing real particles, and discovering that the universe doesn't bend on this. It's not that light is fast, it's that light sits on a different category of trajectory. Objects with mass live in a regime where slower than c is mandatory. They can rest, they can have a frame, they can say, I'm here and the world is moving around me. Light can't do that. A photon can't be brought to rest. You can't ride alongside it and wave. There is no valid photon at rest perspective, which means the speed of light boundary isn't just a speed you can reach with more effort. It's a dividing line between two kinds of existence in space-time. Massive things, you always have time. Massless things, you always have c, and the universe won't let you swap membership. Now, there's a subtle twist here that makes the wall feel even colder. In everyday language, mass sounds like, how much stuff is in the thing? But in modern physics, mass is better understood as a kind of built-in energy, a rest energy. It's the part of your energy you can't get rid of by changing your motion. So, when you try to accelerate something with mass towards c, you're not just asking it to move faster. You're trying to force an object with rest energy into a trajectory that only massless objects are allowed to occupy. That's why the price explodes. Because you're asking space-time to do something, it treats like a category error. And that's also why the universe gives you a weird consolation prize. You can get absurdly close. Close enough that, for many purposes, the difference doesn't matter. Close enough that particles and accelerators live in that near-C world all the time. But close enough is not equal. Because at the boundary, the math doesn't just get difficult, it breaks, which is exactly what a fundamental limit looks like. And now that we've built that wall, now that you can feel how absolute the vacuum speed limit really is, there's an obvious question that sounds like a loophole. If mass can't reach C, why does light sometimes seem to move slower than c in water, glass, or diamond? Here's the loophole that makes people feel like they caught physics slipping. You've heard it before. Light slows down in water, in glass, in diamond, in fiber optic cables. The number changes, sometimes dramatically. So, if light can be slower than the speed of light, doesn't that mean the speed limit isn't real? It sounds like a crack in the rule. But it's not, because what slows down in matter isn't a lonely photon dragging its feet through syrupy space. What slows down is the signal, the wave front, the overall march of electromagnetic disturbance through a material that's packed with charged particles. A vacuum is empty in the way physics cares about. There's nothing there for the light to continuously negotiate with. A material is the opposite. Even the clearest glass is a crowded city at the microscopic level. Electrons bound to atoms, ready to respond the instant an electromagnetic wave shows up. When light enters that city, it doesn't just glide through untouched. It interacts over and over, and those interactions cost time. A clean way to picture it is like this. The light doesn't lose the speed limit. It keeps getting briefly interrupted. The material's electrons get nudged, they jiggle, they re-radiate, and the re-radiated wave adds to the wave continuing forward. The net result looks like the light went slower. But what actually happened is that the signal took a path full of microscopic delays. Not because the photon suddenly has mass, not because the vacuum speed limit got rewritten, because the medium forced the message to take detours. It's the difference between a car's top speed and your average speed in traffic. Your engine might be capable of 120 miles an hour, but if you're hitting lights, stop signs, congestion, merges, and construction, your average speed collapses. Nothing about your car's fundamental limit changed. The environment changed the journey. That's what refractive index really is, in plain terms. How much the material makes the electromagnetic wave spend time interacting with it. And that's also why the effect depends on wavelength. Different colors of light interact differently with the structure of the material. The delays aren't identical for every frequency. That's why prisms spread white light into a spectrum, because the traffic pattern isn't the same for every color. Now here's the detail that matters for the speed limit story. Even when light slows down in a medium, it's still not breaking the cosmic rule, because the cosmic rule is about vacuum, about the structure of space-time itself. Inside matter, you're no longer talking about the clean, fundamental propagation limit. You're talking about how a complicated system relays a signal through a forest of charges. And yes, sometimes we do insanely clever things in laboratories that make light appear to crawl. People have slowed pulses to walking speed in exotic conditions. But again, that's not a photon violating the vacuum limit. That's a pulse being stored, reshaped, and re-released by the medium, like handing a message through a line of people. The message can move as slowly as the line decides, without changing the fastest possible speed that information can travel through empty space. So the rule stands, untouched. In vacuum, C is the ceiling. In matter, you're watching the ceiling through a maze. And once you absorb that, once you separate vacuum limit from medium delays, you're ready for the strangest twist of all. The universe doesn't just set a limit. It insists that everyone measures the same limit, even when they're moving. Imagine you're standing on a moving train with a flashlight in your hand. You point it forward, down the aisle, and you click it on. Common sense tries to do the math immediately. If the train is moving and the light is moving, shouldn't the light's speed add on top? Like tossing a baseball from a speeding car, your throw stacks with the car's motion. People in the parking lot see a faster ball than the person in the passenger seat. So, you'd expect the same for a beam of light. If you chase a beam at half the speed of light, 0.5 c, then from your perspective, the beam should crawl away from you at 0.5 c. That's what your intuition screams. But when physicists actually test it, something almost insulting happens. You still measure c, not c minus your speed. Not c plus your speed, just c. And this is the moment where the universe stops behaving like a normal place. In the late 1800s, scientists were so confident that light must travel through something, a kind of invisible ocean, that they gave it a name, the luminiferous ether. The idea was simple and comfortable. Sound needs air, waves need a medium. So, light should need a medium too. If the ether existed, then Earth, moving through space, would be plowing through this ether all the time. That motion should create an ether wind. And if there's an ether wind, the speed of light should look slightly different depending on whether you measure it along the wind or across it. That difference would be tiny, but not zero. So, two scientists designed a brilliant trap. Albert Michelson and Edward Morley built an instrument called an interferometer. Basically a light-based ruler, so sensitive it could detect absurdly small timing differences. They split a beam of light into two perpendicular paths, bounced the beams back, and recombined them to create interference patterns. If one path took even a hair longer than the other, the pattern would shift. They rotated the device. They tested different times of day, different seasons, as Earth's direction of motion changed around the sun. They were hunting for that ether wind like a ghost hunter with a flashlight in an abandoned house. And the result was the most terrifying kind of result in science. Nothing. No shift. No wind. No ether. The speed of light refused to change. That should have been impossible under the old rules. Because if there's no medium and no preferred rest frame of the universe, then what is light using as a reference point? What is it measuring itself against? This is where most people think Einstein did something like magic. But what he actually did was more daring than magic. He took the results seriously. He didn't patch it. He didn't say, maybe the experiment missed something. He said, fine, then the universe is telling us something radical. Einstein's special relativity begins with a simple, ruthless idea. The laws of physics are the same for all observers who move at constant velocity. No hidden true frame. No cosmic background that tells you who's really moving. And then the second idea lands like a hammer. The speed of light in a vacuum is the same for all observers, no matter how fast they're moving. That's the constancy of c. And if you accept those two statements, you don't get to keep everyday notions of time and distance. Something has to give. It's like trying to keep two promises that seem to contradict each other. If motion doesn't change the measured value of light's speed, then the universe has to compensate somewhere else. Not by slowing light down, not by speeding it up. by reshaping your measurements of space and time themselves. This is why special relativity doesn't say, light is weird. It says, your intuition about time and space is incomplete. Because if every observer, on every train, in every spaceship, measures the same c, then simultaneous can't be universal. Two people moving relative to each other won't agree on what events happened at the same time. It's not a philosophical quirk, it's a mathematical consequence. And the price of keeping c constant is paid in two currencies that feel almost personal. Time can stretch, distances can shrink, not as illusions, not as bad clocks, not as warped rulers, as real properties of how space-time behaves when you're moving. This is why the train and flashlight thought experiment isn't just a cute classroom trick. It's the doorway. It's the point where the universe forces you to choose. Keep your old picture of time and space, or keep the measured facts. Einstein chose the facts. And once you do that, the speed of light stops being the speed of a thing. It becomes a built-in conversion rate between space and time, a constant that reality refuses to negotiate. So, when you hear the claim, everyone measures c, don't hear it as a technical detail. Hear it as a warning label. Because if c is constant in every frame, then the universe has a deeper rule underneath motion, one that makes some events feel like they happen too fast, while still never letting information outrun causality. And that's exactly where things start to look like the universe is cheating, even when it isn't. People hear, nothing can go faster than light, and their brain immediately starts looking for escape hatches. Because the universe is huge, it's violent, it's weird, and we've all seen headlines that sound like the speed limit is being broken. So, this is where the story gets dangerous in a fun way, because there's a whole gallery of phenomena that look like they're sprinting past c, and if you don't understand the trick, it feels like physics is lying to you. But the trick isn't cheating. It's something sharper. It's that relativity is not primarily a rule about speed. It's a rule about cause and effect. And the universe will let you watch the illusion of faster than light from every angle, as long as the illusion can't be used to send a message into the past. So, let's walk through the gauntlet, the 5 big loopholes people bring up, one by one, and you'll feel the pattern. Not a list, a pattern, because every time it looks like c is being violated, the same question returns like a judge's gavel. Can you use it to transmit usable information faster than light? If the answer is no, then causality survives, and relativity stays undefeated. The first one is the one that feels the most like magic. Entanglement. Two particles interact, then they're separated. One goes left, one goes right, far apart, maybe light years apart. And somehow, their measurements stay linked. If you measure one, the other knows. It's the kind of statement that makes your stomach drop because it sounds like a secret phone line outside space-time, like the universe is whispering. And to be fair, this isn't pop science fluff. This is real. We've tested entanglement in labs, across cities, even using satellites. The correlations are there. They're stubborn. They refuse to be explained by any simple, hidden note the particles carried in their pockets. So, doesn't that mean information is traveling instantly? Here's the part people miss. The outcome you get when you measure your particle is random. Truly random, at least as far as any experiment has ever been able to show. You can't choose it. You can't steer it. You can't decide, I'm going to encode a 1 by forcing spin up. You measure and you get what you get. Only afterward, when you compare notes with the other observer, using an ordinary slower than light channel, do the correlations pop out. Entanglement gives you a relationship between results, not a controllable signal. It's like two people flipping coins on opposite sides of the earth, and later discovering the coins match in a strange way. That discovery can feel spooky, but it doesn't let either person send a sentence through the coin. So, yes, entanglement is instant correlation. But no, entanglement is not instant communication. Causality remains intact. The speed limit stays unbroken, not because the universe is being conservative, but because the universe is being consistent. Now, the second loophole is the one that feels like it should be illegal, the expansion of space. Because here's a fact that sounds like science fiction. There are galaxies so far away that, relative to us, they're receding faster than the speed of light. And that's not a misprint, so what gives? The key is one phrase that changes the whole frame. They are not moving through space faster than light. Space itself is stretching. Relativity doesn't forbid the distance between two far-away points from increasing faster than c, because that increase is not a local motion. It's not a rocket accelerating past the limit. It's the metric, the ruler of space-time, changing. This is why cosmologists can talk about superluminal recession without setting physics on fire. It also explains the weirdest consequence of all. There are regions of the universe that are visible to us only because the light was emitted long ago when those regions were closer. But due to expansion, light emitted from them today may never reach us. Not because light got tired, because the intervening space keeps stretching like a treadmill that accelerates forever. So expansion can produce faster than light separation. But it doesn't let you send a message faster than light, because any message you try to send still has to travel locally through space-time. And locally, the rules don't bend. You're still stuck with C for actual cause and effect propagation. The third loophole is one you can practically see: Cherenkov radiation. That eerie blue glow in nuclear reactors. It looks like science fiction aura, like the reactor is haunted. And the explanation that gets tossed around is usually this: a particle is moving faster than light, which sounds like the end of relativity. But the phrase is missing a crucial clause: faster than light in that medium. Light's speed in vacuum is the cosmic limit. But light traveling through water, glass, or any material doesn't move at c as a wavefront. It gets delayed by interactions, by the microscopic structure of the medium, so its effective speed is lower. And particles, electrons for example, can indeed move through that medium faster than the slowed down light wavefront can. When they do, they create a shock wave of light, the same way a supersonic jet creates a shock wave in air. Not because the jet broke the universal speed limit, but because it exceeded the local sound speed in that medium. So, Cherenkov radiation is the optical version of a sonic boom. It's real, it's dramatic, and it doesn't violate relativity because the particle still isn't outrunning c in vacuum. The speed limit survives again, because it was never defined by water in the first place. The fourth loophole is the one that messes with people who grew up hearing, light is always fast. Slow light, even stopped light. There are experiments where scientists pass light through exotic materials, cold atomic gases, special crystals, and the light pulse crawls along at bicycle speed. In some setups, it can be stored and released later, like the material is holding the light in a kind of pause. So, did we just turn down the universe's speed limit knob? Not exactly. In these experiments, what's moving slowly isn't a lone photon lazily drifting through space. What's happening is more like a relay. The light pulse couples into the material, becomes a shared excitation, part light, part matter, then couples back out. The information in the pulse is being carried by a system that includes the atoms themselves. It's not light ignoring C. It's light handing off its presence through a medium in a way that delays the wave front. And just like before, none of this lets you send a controllable message faster than light in vacuum. If anything, it slows things down. It's a detour, a clever one, a beautiful one, but not a jailbreak. Now we get to the fifth loophole, the one that people love because it sounds like a clean punch through the rule: quantum tunneling time. You may have heard the phrase, tunneling can be instantaneous, or particles can appear on the other side of a barrier with no time spent inside. And depending on how you define the timing, certain experiments do produce results that look suspicious, like the particle didn't cross the barrier in the ordinary sense at all. So, is that faster than light travel? Here's the problem. In quantum mechanics, the idea of how long did it take inside the barrier is not as simple as timing a runner on a track. The particle doesn't follow a classical path through the barrier. The barrier region is exactly where the normal picture breaks. Some definitions of tunneling time can come out very small. Some can be weird. Some can suggest a kind of apparent superluminal behavior, especially when you measure the peak of a wave packet and notice it seems to emerge sooner than expected. But then you ask the same ruthless question again: can you use tunneling to send information faster than light? And the answer, once physicists put it under the microscope, is no. Because the part of the signal that carries new information, the leading edge, the front that tells you something changed, does not outrun C in a usable way. The reshaping of the wave packet can make the peak appear early, like a magician pulling a card out of the deck before you think he had time. But the magician isn't changing the laws of time. He's using the structure of the deck. In tunneling, the structure is the wave packet and the barrier filtering it. You can get an illusion of speed from reshaping, but you don't get a controllable causal channel that beats the limit. And when you measure carefully, the story becomes less like instant travel and more like quantum behavior doesn't map cleanly onto classical timing. Spooky? Absolutely. A loophole that lets you build a faster-than-light phone? No. If you step back, the gauntlet starts to look less like a pile of exceptions and more like a test of what you really mean by faster than light. Because you can have correlations that appear instant but can't carry a message, distances that grow faster than c but aren't local motion, particles that outrun light in a medium but not in vacuum, light that slows down in matter but only by taking detours, tunneling that seems too fast but won't let you break causality. Every case feels like rebellion, and every case ends the same way. Relativity doesn't care about your feelings. It cares about whether cause can outrun effect. As long as the universe prevents you from sending a usable signal that arrives before it was sent, the deeper rule stays unbroken. And that's why these faster-than-light stories are so valuable. They don't weaken the speed limit. They teach you what it actually is. Not a restriction on motion like a traffic law. A boundary on reality's ability to remain logically consistent. So, when someone says, maybe we found a loophole, you can smile, because physics has been through this trial again and again, and the speed of light keeps winning. Which sets up the next question beautifully. If all these things only look faster than light, what would happen if something truly was faster than light? Because that's where the universe starts to do something even stranger than bending time. It starts to threaten the order of time itself. There's one idea that sits on the edge of physics, like a horror story people keep retelling. Not because we believe it, but because it shows you exactly what's at stake. Imagine a particle that can't slow down to the speed of light. Not sometimes faster, or not under special conditions. Always faster. That hypothetical creature has a name, a tachyon. And the moment you say the word out loud, the universe starts to feel unstable. Because tachyons don't just threaten the speed limit, they threaten the order of events. Here's why. In relativity, different observers, moving relative to one another, don't always agree on the timing of two separated events. They can argue about how much time passed, and even about whether two far apart events were simultaneous. But they do agree on something sacred. Cause should come before effect. Tachyons punch a hole in that agreement. If a signal could travel faster than light, then for some observer, moving at the right speed, what looks like message sent, message received, can flip into message received, message sent. It's not just weird, it's a paradox factory. Because now you can build the classic nightmare. A message that arrives early enough to prevent itself from being sent. A reply that shows up before the question. A chain of events with no stable beginning, like a sentence written in the air with no hand holding the pen. That's why tachyons are often used as a teaching tool. They're a stress test for reality's logic. And when you run the test, the verdict is brutally consistent. If tachyons could carry controllable information, causality becomes negotiable. And once causality is negotiable, physics stops being a rulebook and starts being a choose-your-own-adventure that contradicts itself. So, what do physicists actually think? Most treat tachyons as a signpost, not a destination. In modern theories, tachyon sometimes shows up mathematically as a warning light, an instability in a model, a signal that the system wants to settle into a new, calmer state. Not a real faster-than-light particle you can bottle or beam across the galaxy. In other words, Tachyons are the universe's way of reminding you that the speed limit isn't a preference. It's the guardrail that keeps time from tying itself into knots. And then, once in real life, everyone held their breath. In 2011, a team working on a neutrino experiment in Europe reported something that sounded almost illegal in the language of physics. The neutrinos seemed to arrive a little too early, not by minutes, not by seconds. By a tiny sliver, tens of nanoseconds, but enough to whisper the unthinkable. Faster than light. For a moment, it felt like the floor moved. Because this wasn't a late-night forum post or a half-baked headline, this was careful equipment, long baselines, timestamps, a measurement that, if true, would tug on every thread we'd been pulling for a century. And here's the part most people miss. The scientists didn't declare victory and build a religion around it. They did something much more unsettling and much more beautiful. They doubted themselves first. They opened their own result like a watch. They checked every assumption that usually hides in the background. Cables, clocks, calibration, synchronization, delays inside electronics, tiny offsets that feel too small to matter, until the claim is faster than light. And suddenly nothing is too small. Other teams looked too, because physics doesn't settle arguments with confidence. It settles them with replication. And as the dust cleared, the miracle shrank into something painfully ordinary. A mundane hardware and timing problem. A connection that wasn't behaving the way everyone assumed. A system-level detail that can bend a measurement by a whisper, exactly the size of the breakthrough. When that was corrected, the speed limit snapped back into place. No conspiracy, no embarrassment to hide, just the real process. A bold result put on trial, cross-examined by reality, and revised when the evidence demanded it. That's the lesson that matters more than the headline. We don't treat C like a sacred number. We try, over and over, to knock it off its pedestal. And every time we run at it with better clocks, cleaner experiments, and sharper skepticism, it holds. Which is why the speed limit feels less like a rule we invented, and more like a rule the universe keeps enforcing. And if you want to see the harshest enforcement of all, you don't look in a lab. You look at the place where space-time itself draws a boundary, where even light can't argue its way out. Picture the speed limit as a rule painted on the road. Useful, familiar, but a black hole is where the road itself bends. And the rule stops feeling like a sign you could ignore and starts feeling like a law of geometry. Far from anything massive, escaping is simple. You move away, and space mostly behaves. But as you fall towards something extremely dense, gravity doesn't just pull on you like an invisible hand, it reshapes the directions you're allowed to travel. Here's the cleanest way to feel it. In ordinary life, you can always choose a path that points outward. You can always point your motion away from the source. With enough energy, enough speed, enough patience, you can leave. Near a black hole, that freedom gets squeezed. Not because there's a physical wall, not because light gets tired, but because the future itself starts leaning. In Relativity, you can imagine your future like a cone of all possible directions. You can move in, forward in time, in all the ways your body and the laws of physics allow. In calm space-time, that cone stands upright. Forward means you still have options. A little left, a little right, upward, outward. Your tomorrow includes escape routes. As you approach a black hole, space-time tilts those cones inward. The closer you get, the more forward points toward the black hole, the way rainwater on a sloped roof has fewer and fewer options until it must run downhill. You can fight it for a while. You can fire rockets. You can scream "not today" into the void. But the slope keeps steepening. Then you reach the boundary where the tilt becomes absolute. That boundary is the event horizon. And it's not a surface you crash into. It's a line in the geometry of space-time where outward stops being a direction you can take into the future. People often say, the escape velocity becomes the speed of light. That's a good intuition because it captures the punchline. To get out from that close, you'd have to move faster than C, and nothing that carries information, nothing that can cause effects, gets to do that. So, the horizon isn't a wall that traps light the way a cage traps an animal. It's a causal boundary. It's the point where every allowed future path points deeper in. Light doesn't refuse to leave. It can't find an away that still points into tomorrow. That's why black holes are terrifyingly honest about the speed limit. They don't just remind you that you can't outrun light. They show you that you can't outrun causality. And then physics adds one more layer, one that feels almost like a whisper in the dark. Because black holes aren't perfectly black. When you take quantum ideas seriously near that horizon, you get a faint, slow leak of radiation, what we call Hawking radiation. The intuitive picture is not that something blasts out from inside the hole like a flare. It's subtler. The vacuum near the horizon isn't quiet in the quantum sense, and the horizon complicates what different observers mean by empty. The result is that, over unimaginable time scales, black holes can lose mass. That's not a loophole that lets messages escape from inside. It's more like the universe charging a tiny interest payment for the existence of a horizon at all, a slow accounting of energy, written in the language of quantum fields and curved space-time. And we've seen the shadow of this geometry with our own eyes. When the Event Horizon Telescope stitched together data from Earth-sized baselines, it produced an image of a bright ring wrapped around a dark center, an eerie donut of light. That brightness isn't the surface of the black hole. It's hot gas and plasma whipping around at insane speeds, light being bent, lensed, and piled up by gravity right at the edge of what can still reach us. The darkness at the center isn't paint. It's a region of space-time where light paths curve inward and fail to return, a visible absence shaped by the speed limit. So, when we talk about black holes, we're not just telling spooky stories about cosmic monsters. We're pointing to a place where the rules stop being philosophical and become architectural, where the universe demonstrates, with brutal clarity, that there are directions you cannot go, not because you lack effort, but because the map itself forbids it. And once you accept that, one last thought lands with a quiet weight. If light can't cross certain boundaries, then every look into the universe is already a look into the past, because even in open space, light takes time to reach you. Which means the speed limit doesn't just shape black holes, it shapes what you can ever know. Look up at the night sky, and it feels like you're seeing now, like the universe is happening in real time, right in front of you. But the truth is quieter and stranger. You're seeing history. Every photon that reaches your eyes is a survivor of distance. It left a star, a galaxy, a cloud of glowing gas, and it spent time crossing the dark in between. So, the sky is not a live broadcast. It's an archive, a museum where the exhibits are made of light and the labels are measured in years. And the deepest exhibit in that museum is the cosmic microwave background. The CMB is sometimes called the universe's baby picture, but that phrase doesn't fully land until you imagine what it means. It's not a photo of a galaxy. It's not even a photo of stars. It's a snapshot from a time before stars existed. Early on, the universe was a hot, opaque fog, charged particles everywhere, light constantly colliding, unable to travel freely. Then the universe cooled just enough for electrons and protons to settle into neutral atoms. Suddenly, the fog cleared. Light could finally move without being immediately scattered. Those first free photons have been traveling ever since. Over billions of years, the expansion of space stretched their wavelengths, cooling them down into microwave light. So faint, we don't see it with our eyes, but real enough to measure with exquisite precision. When satellites mapped that glow, the universe revealed a pattern. Tiny temperature differences, tiny ripples. Slightly warmer here, slightly cooler there. The Planck map made those ripples famous, a delicate modeled fingerprint of the early cosmos. And those tiny variations are not trivia. They're the seed crystal of everything. They're the faint unevenness that gravity later amplified into galaxies, clusters, and the large-scale structure of the universe. Without those microscopic imperfections, matter wouldn't clump, stars might never ignite, there would be no chemistry complex enough to write stories, or to listen to them at night. But there's another twist hiding inside the CMB, and it's the one that makes the speed limit feel almost emotional. There is a horizon. Not a wall you could fly into, not a boundary drawn in space, a horizon drawn in time. Because the universe has a finite age, light has only had a finite amount of time to reach us. That means there are places so far away that their light, no matter how fast it travels, has not had enough time to arrive yet. And even more haunting, because the universe's expansion is accelerating, there are regions whose light will never reach us, even given an infinite future. The space between us and them stretches too quickly. Their messages fall behind, like a runner trying to sprint upstream in a river that's speeding up. So, as the universe ages, the accessible universe can effectively shrink. Future astronomers, billions of years from now, may see less than we do. The sky could become lonelier, not because the universe empties out, but because the speed limit and expansion together can hide it. And scientists have tried to see if the speed limit ever wobbles at extreme energies, using distant explosions and gamma-ray bursts as test signals, watching for tiny arrival time differences that might hint at quantum gravity effects. So far, the verdict is stubborn. The limit holds. The rule keeps surviving every new attempt to break it. Which brings us right back to the question that started all of this. Because if the universe can preserve a speed limit across billions of years, across the whole visible sky, then that limit isn't just a number. It's the rule that decides what can be known, what can be seen, and what can ever arrive. So, let's close the loop, slowly and for real. Light has no rest mass, no fuel tank, no engine strain, nothing to weigh it down, and yet it doesn't sprint off into infinity, because the limit was never a rule written for light. It's a rule written into reality. That number, c, is the fastest that cause and effect can travel, the fastest a because can follow a what happened, the fastest the universe can let one event reach another, and still make a coherent story out of time. Light just happens to sit right on that edge. It's the speed limit made visible, like you're watching the universe enforce its deepest boundary in real time. So, when you click on a flashlight, you're not merely making a beam. You're watching space-time reveal its structure. You're watching the cosmos say, quietly and consistently, this far and no farther, if meaning is going to survive. And if that idea rewired something in your head tonight, I'd love to hear it. Drop a comment and tell me, did this change the way you picture space, or time, or what speed even means? And if you're listening from bed, tell me what country you're in and what time it is right now, because I always love seeing how far this little signal travels. If you want more gentle journeys like this, you can tap like and subscribe for new stories that take big physics and make it feel human. For now, let your shoulders soften. Let the day loosen its grip. You don't have to solve the universe tonight. Just rest. Good night.